What's in the box? This is the Jetson AGX Thor developer kit. This is what's in mobile autonomous robotics systems, or at least this is the building block of a possible platform for autonomous robotics, an experimentation platform for things like self-driving cars or robots that automatically do things. There's 128 gigabytes of high-performance Blackwell in this box because of the label on the box. So we're going to unpack this and try to run developer things on it. But also, if you're a developer and you want to run things on it, hit us up in the forum at Level 1 Techs because that's what we do. It's a squeaker. Nvidia calls this the platform for humanoid robotics. A developer's tool, a robot brain, if you will. A robot brain in a 120 watt power envelope, purpose-built for high-performance video and sensor data processing with extremely low latency because all of the processing happens here. But as I started testing this thing, something clicked. I began to really understand what NVIDIA's talking about when they say the three computers for physical AI. So here's the plan. I'm going to try to show you this and break down the hardware. I'm going to dive into NVIDIA's i6 Sim Lab and the Groot ecosystem. I am Groot. Yeah, I am Groot. And what this ecosystem might enable you to do from a robotics and integration, like integrate this into your product kind of a thing. So this is a piece of hardware and the stuff that you can run on here and all that is all well and good and it's interesting. But I think that actually the larger story here isn't this piece of hardware. It's the developer experience for the ecosystem, the larger ecosystem. This is just a brick in that ecosystem. I want to explain this because I get NVIDIA's three computers in a way that I didn't get it before. And honestly, this might be the more remarkable aspect of this than just the hardware itself. But in order to understand the grand scheme of things, you got to understand the hardware. All right, specs first. This looks like a mini PC, and it kind of is. But for robotics, inside this is really the developer kit. It's a Jetson T5000 module that's down here. And this packages that module with a heatsink. That's this. It's like half the thing here. An I.O. module, a bunch of I.O. ports, an NVMe SSD, an NVMe wireless card. It's packaged. The T5000 is packaged to make it easier for developers. And just so you know, this is physically the same as past Jetson modules, but electrically it's not the same. So it is a little different there. It's evolving. I suspect everyone watching this has also heard of DGX Spark. Now that's NVIDIA's hotly anticipated ARM mini PC, the one that they've talked about. You're going to be able to do all kinds of AI smarts. This is kind of like Spark, but it's not Spark. It's Spark with the AI robotics interface sensor platform. But your expectations for Spark should be sky high based on what you're about to learn about this platform. 2560 CUDA cores, 96 tensor cores. It's a Blackwell GPU. That's up to 2070 FP4 tops. It has 14 ARM Neoverse V3 AE CPUs up to 1.57 gigahertz. It has 128 gigs of LPDDR5X up to 275 gigabytes per second memory bandwidth. DMI decode, 1-bit error correction, which makes sense because you're going to be running mission critical robotics stuff on your T5000 robot brain. One thing, it seems, in Linux at least, the ways that I have to test memory bandwidth actually show less memory bandwidth from the Neoverse cores, 35, 40 gigabytes per second. It's pretty reasonable, nothing to sneeze at. But the GPU side of it, yeah, you can access the 275 gigabytes per second from the GPU side. And this is maybe sort of kind of similar to how AMD built their Strix Halo platform, which I'm sure that a lot of people are going to be interested in a comparison about at some point later. Our build here, as I said, it has an M.2 with 4 PCIe Gen 5 lanes. I've got a 1 terabyte in there. There's also a QSFP port that it can be 4 25 gig E interfaces. Plus it also has physical 5 gig wired Ethernet. And, you know, it can do Wi-Fi and Bluetooth through that 1 lane M.2. Oh, and that QSF port, yeah, that can be 4 25 gig E fiber optic lanes or It's ready to go for Nvidia's sensor platform. Think of it like a fiber optic robotic spinal column. You can use that for interfacing to the rest of the robot body at ultra high speed and ultra low latency. This platform is built for video encode and decode, 6 4K 60 encodes or 4 8K 30 H.265 decodes, and support for up to 20 camera inputs directly with up to 32 virtual channels. It has a CAN bus, controller area network, JTAG, GPIO headers, a debug USB port that's hidden there with magnets and everything that you would expect if you were going to build a humanoid robot in the wild based around those T5000 modules. What about over the Jetson Orin? I mean, that's the older model, right? What kind of upgrade is this? Well, Thor is about 7.5 times more AI performance, about 3.5 times more power efficient, 3 times more CPU performance, and about 10x the sensor input processing capabilities. This is not a small bump. It is an order of magnitude, step that Nvidia promised back at GTC when they said that the future was physical AI. I'm sort of starting to get that. I sort of understand what they're doing with that. But before we get to how we put this in here, let's talk about NVIDIA's simulation Groot Isaac ecosystem. In our demo here, we've got a humanoid robot that can sort nuts. I know it doesn't sound impressive, but it's actually hugely impressive. At first, a human operator teleoperates the humanoid robot. This demo is NVIDIA. They've shown off this kind of thing before, these kind of robots handling various kinds of things and a human nearby, steering wheels, whatever. This demo is something deceptively simple. Take a single nut from a hopper of nuts, place the single nut in a bowl, and weigh it. The human does this a lot of times to gather data. Understand that, I'm wearing a VR headset, and I'm experiencing what the robot experiences. And this is Jetson Thor. Jetson Thor is in the loop. Vision systems, sensor data, motor positions. The Jetson is not doing any computation just yet. It's just observation. Everything is recorded in minute detail. All of the sensor data, the point of view video, the joint positions. This is Groot teleop. Then you, dear developer, you take that data and you upload it into Groot Mimic. That'll take your real data and multiply it 1 million times or more. That's going to generate a large enough data set to actually train a model based on what the human operator did. NVIDIA has a bunch of really powerful jumping off points from here. Groot dexterity. If you have a bunch of complex motors, like there's a robotic hand with you need fine grained dexterity. Groot mobility for movement if the robot is autonomous or can move around a warehouse. Groot control. But the magic one for us is Groot perception. We can integrate vision and language models into what was happening with the person piloting the robot. And as a developer, you can leverage Cosmos and Omniverse to help you. Permutations could include like nut position, lighting, and sometimes 2 nuts fall out of the thing and you have to deal with that. Out of all of that comes a trained model. And here's the magic. That model can now directly run on the Jetson hardware. It's running up there. Here's the thing though, debugging and software bugs, is it too complex to run on this hardware? Like maybe it runs fine in the simulator, but does it run on the hardware? Maybe we have specific latency or performance requirements that's going to depend on real hardware. Well, NVIDIA's got you covered. This is the in the loop aspect from their vernacular. That hardware is literally in the loop. My Threadripper workstation here with an RTX Pro 6000 is running the Isaac Sim environment. Thor is running the Groot in-1 inference model. Jetson Thor thinks that it's connected to real motors and sensors. This is hardware in the loop. We're running our software on Jetson Thor up there, even though we don't have a humanoid robot yet. We're simulating it. We're using our workstation to simulate the hardware and to make sure that it works and performs as expected. So we're literally and figuratively testing the model running on the hardware that it will run on. So you can simulate endlessly from your workstation, faster, cheaper, safer, and then deploy on real robots with the exact same code. This is the same, T5000 module running real hardware or simulated hardware. There's no hand waving here. It's the same thing from a software developer's point of view. Hardware in the loop or software in the loop, depending on what your needs are, is not a problem. That's the loop that NVIDIA has been talking about. Developers have a much easier time setting up test fixtures, automating testing, model evaluation, like how good did the training go? Maybe there's some bad data in the training information and we need to figure that out. That's going to reduce time to market, complexity, overhead, you name it. That aspect of this is what has so much potential, even more so than what I see in just the hardware by itself. I mean, the hardware is fun and it's a lot of fun to build robots, but the platform has longevity implications far beyond this particular iteration of the hardware. And that ties into their big idea. That's the 3 computers of physical AI. Training on DGX AI supercomputers. Those can be on-prem, but more typically in the cloud. Simulation and validation using Omniverse and Cosmos models via RTX Pro, workstations, servers, whatever you need for that kind of simulation. And finally, deployment here on, your T5000 Jetson module. You've just seen all 3 components of that vision working in concert to make this kind of development at an automation pipeline accessible basically to anybody with an idea. Now, almost everything that I've done here, from pulling Isaac Sim to running Groot in one and then Cosmos Reason models, it's just Docker containers and Gradio UIs. Run the container, attach to it, and you're live. You're ready to rock. And that's really all there is to it. Jetpack 7 ships with Ubuntu 24.04 and a preemptible real-time kernel. You also get multi-instance GPU support. That means that you can partition the GPU resources, Vision one side, large language model on the other, and that helps prevent resource contention because it is a physical partition. You can deal with that however makes sense for your application. The QSF port, as I was mentioning, HoloScan sensor bridge for low latency and multimodal sensor streaming. That's something you might want to look into. It's also drop-in ready for FPGA applications for advanced users. If you're into the FPGA stuff, it's there. And Nvidia has blueprints for a lot of things, including video search and summarization. This is where you can drop in a video feed or even do a live video feed and then literally ask questions like, did the worker wear PPE, personal protective equipment? Or which shelf did the box go to or come from? And the model can answer. It's shocking how polished this stack is. Check this out. Just more Docker containers. This is the NVIDIA video search and summarization blueprint without a lot of changes. We can start by telling the video analysis pipeline the kind of object classes that we're interested in. People, boxes, whatever. And then we can ask yes-no questions when there are things in the video stream present that match those classes. In this case, I'm saying, look for people. And for the people that you see, do they have personal protective equipment on properly? Then, as the video of our warehouse comes in through the day or whatever, we get a table of events where a person was detected. And the system automatically asks itself the question that I had given it, and this is all plain language stuff. In this case, our test clip has someone dropping off a box and then someone else coming and picking up the box later. This is a true false output in this table. That's what the true and the false here means in this table. Now, in the first clip, the person is wearing a hard hat and a vest. And if I click on the chat icon here, it will give us that. This is Gradio. This is a Gradio UI. This is open source. You can build this. You can also ask it other questions. Things like, which shelf did the box come from, or which shelf did the box go to? If you look in the video there are labels, A, B, C, D, E. It knows that it came from shelf E. That wasn't something I was pre-looking for, but it is something that I can ask the AI, which is very interesting. For the other entry in this table, false, a short time later, somebody else comes along and picks up the box that someone else dropped off. They are not wearing PPE, and so that's why that it's labeled as false in this box. But you can ask other questions. You can ask what color shirt they were wearing. You could create a much more complicated model from this. But understand that all of this is just running locally on this device. It doesn't have to. You could actually run this on a Blackwell workstation, which would be overkill. And you got a lot more power and thermal envelope and that sort of thing on a desktop computer. But for a video analysis thing, or if you had an autonomous robot that was patrolling a warehouse or something like that, you can get creative. There's a lot of flexibility here. This is a demo kit. This is something you're meant to take and run with as a developer. Use this as a starting point. This whole time sitting here running with these Docker containers experiments, I kept thinking, this is kind of like the Raspberry Pi ecosystem, is it not? I mean, isn't this how that evolved? I mean, think about it. NVIDIA's facing competition on the let's do math on silicon aspects of the hardware. I mean, competition is relentless and margins are high, so they're going to be even more relentless. And even the cracks I think are showing in, CUDA, from CUDA 11 to 12 to 13 across hardware generations. It was not always the promise of portability quite as cleanly as it should have been. But what keeps everybody cemented in the Raspberry Pi ecosystem is the software side of it. I mean, that's not the best tiny little low power mini computer for that thing. It's a lot of fun for developers, and it's a lot of, there's a lot of exciting things happening there. And that's what made me think of that for this, is like, there's a lot of really exciting things here. I mean, Jetpack as a name makes sense. You've got a Jetpack's worth of developer momentum if you start with this and use this as a platform to build your solution. You're going to have all that momentum. And I think that, I was expecting to be able to poke more holes in this, but it's really quite astonishing how polished and well put together this is already at this relatively early stage. So what about generative AI and uses outside pure robotics? Well, this platform can do that too. I mean, if you look at, our Llama 3.1, 7 billion parameter here, we can hit about 150 tokens per second. And this is all local and offline. A 32 billion parameter model, about 79 tokens per second. Even this 70 billion parameter version of Llama, it's about 12 tokens per second. That makes, if you do the math, 128 gigs of memory, 275 gigs of memory bandwidth, makes sense in our 40 to 130 watt power envelope. Oh, and for reference, Orin would get you about 16 tokens per second on the 32 billion parameter model. So we're talking like a 5x uplift in real throughput. Now, this platform, though, isn't about just running an LLM on a small model. I share these numbers with you to give you an idea about the relative performance that you may have already experienced and how that works. You should think of this model like the hardware as like finding a balance between relatively smaller models that can run here locally and how useful they are, but also processing sensor information in real time, visual and real sensor, motor position, and to be able to build a platform that you can interact naturally with as a human operator. Very low latency exchanges. The low latency, because it's running locally, makes it feel much more natural. And the local functionality without depending on the cloud and that sort of stuff, which would add latency. So there are already 2.2 million developers in this ecosystem. And I get why it might be about to explode, because I was surprised how relatively straightforward and low effort it was to get up and running with these very advanced solutions. I mean, I'm going to be able to build a malcontented, misanthropic AI dot matrix printer / camera operator. Think of it as a Cambot, Marvin, and R2D2 all rolled into one. What's that, dot? Timmy fell down a well. What does a bag of meat have to do with, dot. That's not very kind. So to recap, Jetson Thor is a compact Blackwell platform designed for physical AI. The Isaac SimLab plus Groot, that whole ecosystem, collect data, simulate it at scale, multiply real physical data with simulated data. It can all handle that seamlessly. I had been much more skeptical about this because I didn't really think that we were on the precipice of an explosion of physical AI. But now that I see how easy and accessible all this has been for me setting this up and getting this running on my own stuff, this might be another frontier. This might even be a more coherent path towards serious productivity gains for AI versus something that is purely generative AI, simply because the developer stack is shockingly approachable and aligns with modern best practices. It's easy to see how test-driven development and like modern DevOps methodologies and those workflows are going to slot right in with physical robots now because of the ecosystem that Nvidia is providing. And the level of polish here is unexpectedly high. Just the foundations of an ecosystem here. If Nvidia is going to maintain its competitive lead with competitors catching up fast in terms of teaching sand to think, okay, maybe, but I'm really not sure that those competitors are even thinking yet in terms of whole AI ecosystem type pathways. And this really, I think, demonstrates that. This really does feel like a possible, Model T moment for robotics. If Nvidia captures developer momentum with their vision of what this should be, then the future here really, really is going to be wild. I don't know what to make of it. I'm Wendell. This is Level 1. If you have any questions or you want to run a simulation or get any ideas for fun GitHub projects that I can pull in and start running and, have a lot of fun beyond a malcontented dot matrix printer, hit me up in the forums. I'm signing out, and I'll see you there.